Alrighties, good morning. This is just a quick volume check for the start of the recording, and we'll get started in 75 seconds. Okay, good morning. Let us start. Alright, so there are two warm-ups here. The first is to find the antiderivative of 3 times t to the 3 to the 10th dt. So don't let the t's bother you. I mean, if the t's were both, excuse me, if both the t's were x's, do the same thing that you'd normally do then. If the t and the t, both here and here, were u's, same general process. And then the second one is to find yet another antiderivative, so that's to find the antiderivative of 1 over 3x plus 10. The thing about the first warm-up is that, let's see, it's tempting to want to do this new method of substitution. The thing is, you can, I mean, if you wanted to show some work at all, you could bring the 3 in front of that integral. But then you have to anti-differentiate t to the 10th. There's no u equals business here. It's just take the exponent 10, raise it up by 1 to 11, divide by that exponent, and there's a final answer. And the method of substitution was not used at all in this problem. The second warm-up question is antiderivative of 1 over 3x plus 10 dx, and this one does require substitution, so it's helpful to substitute using u is equal to the denominator here, 3x plus 10. You might say, well, the derivative then is 3, but I don't see that elsewhere in the problem, and this is where sometimes this hint kind of breaks down a little bit of what's a good selection for you, right? So this is a good selection for you, even in spite of the fact that 3 isn't found elsewhere in the problem, that this 3 would already be accounted for. But the thing is, the fact that this 3 is probably not going to cancel with anything isn't actually that big of a deal, because how should I say this? It's a constant, and it'll probably in some fashion come in front of the integral. So let's solve for dx. We need to multiply both sides by dx. So you have du is equal to 3 times dx, and then one last step to solve for dx, you got to divide both sides by 3. So you have du over 3 is equal to dx. Okay, so then we'll go back to the question which was asked here, the integral of 1 over 3x plus 10 dx, and we'll make some replacements. So the replacements made here, the 3x plus 10 that's down there, we replace it with a u in the denominator, and then the dx was replaced with the fraction du over 3 right here. Okay, so normally after doing the replacements, we try to then do some kind of cancellation, but in this one, we actually, after making the substitutions we did, we don't have to worry about canceling anything because there's already no more x's. So that's good. I'm just going to just slightly rearrange how this one is written to have the integral sign and then the 1/3. So keeping in mind 3 was in the denominator before, so it should remain in the denominator here. And then the 1 over u I wrote next. I just somehow, and then the du, instead of sticking in the numerator of a fraction, is just off to the side. So somehow just kind of organizing it in this fashion. You don't have to, but I just prefer seeing the number and then the function and then the du kind of on its own. Okay, so then the 1/3 is now it's time to anti-differentiate. So the 1/3 is just copied, and then anti-differentiating 1 over u is an ln of absolute value of u plus c. And then finally, as one final step, there's that u right there. We just need to replace it with a 3x plus 10. So as a final answer for the second warm-up, we'll have 1/3 ln absolute value of 3x plus 10, close the absolute value, then a plus c. So the key thing to note between the first warm-up right here and the second warm-up is that the second warm-up question required u substitution. The first warm-up question did not have substitution at all, so there's no u there, right? Not every anti-differentiation problem requires substitution. And here's the thing, even the ones that do eventually require anti-differentiation. So in warm-up 1, we just directly anti-differentiated. In warm-up 2, I highlighted now in this step going from here to here required anti-differentiation anyway. So anti-differentiation happens at some point. It's kind of a question of, does it happen in the middle of the problem, like what usually happens in substitution, or does it happen more or less right away? We could have even skipped past this step and went directly from here to here. But every single one of these problems is going to require anti-differentiation anyway. The whole point of these two warm-up questions is to say that sometimes because of this new substitution thing, sometimes people are so drawn to it and think that it has to be used for every single problem. But in the first warm-up question, substitution wasn't used at all. All right. So hope that looks all right. I'll just pause for a moment, see if we're okay with that. Okay, then a round of announcements. There's an online quiz today. Please keep current with WebWork. What that means for me is to start WebWork 37 today, even if that's not the one due. I would strongly suggest starting WebWork 37. Office hours are here for your reminder. And just as a reminder of the process, we will see today some stranger problems, let's say. Substitution is undoing the chain rule. So not every function was differentiated using the chain rule, but if the function was differentiated using the chain rule, that resulting answer to anti-differentiate, it requires a substitution technique. For you, typically the thing to pick, not always, as we even saw in the warm-up, but the thing to pick is if you see the derivative of u elsewhere in the problem, that's usually a good choice for you. Compute the derivative, compute du over dx, then you solve for dx, and then replace what you had picked for u, replace that where you see that in the problem with a u, and then replace dx with the work from the previous step. You're hoping then at this point the things that need to cancel, and specifically if you're applying algebra cancellations correctly, you're hoping that all the x's go away. If all the x's go away and you have just u's, then that was a good choice of u. If not, go back, pick a different u, and if after picking several different u's it doesn't work, maybe the problem wasn't supposed to be done by substitution, just like one of the warm-ups today. But if all the x's do go away, then you have only u's. So then you need to do that integral that has u's, meaning find an antiderivative, and that was the key thing about the warm-up again, was to say that at some point you will have to find an antiderivative. Don't forget that step. And when you find an antiderivative, you'll need a plus c. And then after having found the antiderivative, this is, I think, a very, picking u is a difficult step for sure. But then I think another key step that is difficult is step 6. So do that antiderivative and then save replacing u with what you said u should be for last. And so, the thing is, people try all kinds of things of doing step 7 before step 6 or trying to combine them. 6 is a difficult enough step on its own. So do step 6, then do step 7. Don't swap the order. Don't combine steps. Don't skip one of those 2 steps. Those are sort of the things that sometimes tend to go wrong. So what I'd like to do is run through this process in perhaps a more challenging problem type than we've seen so far. So I'd like to look at this one. Integral of, or we could say antiderivative of, x to the third times square root of x squared plus 1 dx. Now, off the top of my head, I couldn't think of the derivative of, fill in the blank, is x cubed times square root of x squared plus 1. I wouldn't be able to come up with that, so it's likely that what we need to do is substitution. There's no little algebra manipulation we could do first. Sometimes people think you can distribute the square root, but you can't do that across a plus sign. So let's do a substitution, and I'm going to pick u is equal to x squared plus 1. You might think this is a strange choice. You might have said, well, why not pick u is equal to x cubed, because then the derivative of x cubed is a 3x squared, and ignoring the 3, at least that x squared I see elsewhere in the problem, but the x squared that you'd get from the derivative wouldn't cancel with an x squared plus 1 inside a square root sign because of the plus. So this seems a little strange. This seems like it's not going to go anywhere, but it's going to work out. What I'd like to do is kind of do some of our usual things. Let's compute the derivative of u. So du over dx is equal to 2x. And then, as usual, we need to solve for dx. So let's first multiply both sides of that previous equation by dx. So we'll have du equals 2x dx. And then to solve for dx, divide both sides by 2x. So I hope we're okay so far up to there. The choice made was u is equal to x squared plus 1, even if that seems strange. But making that choice of u equals x squared plus 1, we end up with du over 2x equals dx. We all right there? Let's make a copy of that original question and then replace everywhere that we can. So the replacements I have look like this, right? So integral sign is still there, right here. X cubed is still there. But inside so I copied the radical symbol, but inside the radical, instead of writing an x squared plus 1, I replaced that with the u that we said. And then I replaced the dx here. So we replace this dx with the fraction du over 2x. Here's the thing. We should figure out if anything cancels, and that x cubed, another way to say that is x times x times x. So you've got 3 factors of x in the numerator. You have 1 factor of x in the denominator. That 2x is really 2 times x. So we can cancel one of the x's on top with one of the x's on bottom. And that's why from this step over to this step, it's x cubed and in the numerator and x in the denominator ends up just being an x squared in the numerator. And then I kind of rearranged a couple things. So like the 2 that was in the denominator is still in the denominator. It's a 1/2 here. Sometimes people don't write 1/2, they'll just write a 2 accidentally. But I wrote integral sign 1/2 x squared root u, and then instead of having the du in part of a fraction, I just kind of push it off to the side. But what's wrong with this? What seems to be wrong with this? Any thoughts? What do you notice? What do we think about this substitution up here? Two variables, right? Yeah. So this doesn't look all that promising right now because there's x's and u's. I mean, the hope was to go from a problem, the original problem having all x's, to a new version of the problem. Hopefully we had it here with all u's, and that all of the x's would have canceled out so that we have only u's. Now what? Not all the x's went away. That's what we were hoping for. And I know that under the review of the step-by-step process that we just did a slide ago, the thing was to say, if all the x's don't go away, then you should start over either pick a new u or maybe try something other than substitution for the problem. But there's one last thing we should try. Because there's an x squared here, and let's find another way to write x squared. So take a look from u equals x squared plus 1, from up here, how we had defined u. We had picked u to be x squared plus 1. Let's subtract 1 on both sides of this equation. When you do that, you get u minus 1 equals x squared. Now, in this equation, of course, you could square root both sides, but I don't even want to bother. I don't want to solve for x. I actually just want to solve for, and as strange as it sounds, I want to solve for x squared. The reason I want to solve for x squared is because in this problem, the uncanceled thing, the thing that's left over, the x stuff that we have that we don't want is x squared. So if u really is x squared plus 1, then we can replace x squared with u minus 1. So I made a copy of the most recent version of the problem we have because this other text is getting in the way a little bit. But what we can do is make that replacement. So take a look at this version of the problem and then this next one after the equal sign. You'll notice the replacement that was made was x squared was replaced with u minus 1, and that truly is going to have to be in parentheses due to order of operations here. Are we okay with that step? This is sort of are we okay with where this came from, that it happened to be replacing x squared with u minus 1, and that we were allowed to replace x squared with u minus 1 because we started with u equals x squared plus 1, and if you subtract 1 on both sides. I mean, I just want to make sure, are we cool with this? Okay, I know it's kind of strange, right? But it's sort of like this. Normally we've said all the x's need to go away, and they didn't right away. So instead of kind of just restarting kind of too quickly, there's sort of just one last thing to check for. And I kind of, don't get me wrong, I wanted to talk about this idea yesterday or even the day before when we first introduced substitution, but that would have been too many ideas floating around. So I wanted to do like 2 days where we didn't have any problems that have these shenanigans like we're going to see right now, where we can get used to the overall method and then just point out, sometimes it's good to check for one last thing. So you get to a step like that right over here. If all the x's don't go away, just do one last little thing. See if you can solve for, like in this case, x squared, and then make a replacement. And then we are now at the stage where we have a problem where all the x's have gone away. I would like to just bring the 1/2 in front of the integral sign, and then I'm going to rewrite the root u as a u to the 1/2 power. You don't have to do it this way, but I think it is a little helpful. So the 1/2 is just in front of the integral, right? You can bring a number in front of the integral sign, and then root u I just wrote as u to the 1/2. The reason I'm writing it this way is I want to distribute this u to the 1/2 power. And so when you distribute u to the 1/2 times a u, and you distribute u to the 1/2 times a 1, you have, first of all, u to the 3/2, right? So you're multiplying things with the same base. You need to add the exponent. So when you multiply this u times the u to the 1/2, you're adding the exponents, the hidden exponent of 1 here to the exponent of 1/2, and 1 plus 1/2 is 3/2. And then when you do separately, the other part of your distributing is you multiply 1 times u to the 1/2. Here there's no base of the same, add the exponents business, because the bases aren't the same. It's just 1 times a thing is just that thing. So that's why there's a u to the 1/2 there, with the minus sign being copied from the distributive law. Okay, at this point, we've got 2 separate terms. So That's good when you're anti-differentiating, just like when you're differentiating, when it's terms being separated by plus or minus signs, not by multiplication signs. When it's terms, you can just take care of one term at a time. And so let's anti-differentiate u to the 3 halves. You've got to raise the exponent by 1. So 3 halves, add 1 to it, you have 5 halves. Then you end up dividing by that new exponent of 5 halves. Same deal with this exponent of 1 half. Raise it by 1 to 3 halves, and then you have to divide by the new exponent 3 halves. What I did was, since the 1 half is out here, I surrounded the result of anti-differentiating with parentheses, and then stuck a plus c after. If you prefer, you could distribute the 1 half to this and this, but that's just, like, let's, that's your call. Like, it's not, there's no expectation that you distribute the 1 half or that you don't. You can if you want, you don't have to if you don't want to. Your call. But there's one final thing we need to do in this problem, which is the original question didn't have u's in it. It had x's. So we just, like usual, once we're done with our anti-differentiation process, going from here to there, we just need to now replace all of the u's in this problem with x squared plus 1. So make that one little replacement, and then that's our final answer to this question. So I want to just pause and see if we're doing okay. Or yeah, any questions about any step? I mean, any one step, the explanation is short, so that's why we've got time to answer questions. And it's not so much about the any one step, it's just like there's so many different things going on. It's very, very, very natural for there to be questions. Is there any piece of this process that we can talk about before looking at another example? Would there be another way to solve this if we were stopped when there was 2 variables? Yeah, like over here. Generally, the answer is no, sadly, right? So yeah, that's a good question. It's kind of one of these what if, like just trying to cover our bases. Like it really had to work out. The exponents here and here, in even me designing the question, have to be picked carefully, very carefully, so that the process of going from here to here works out. It almost always does not work. So I have to be very careful designing a problem, if you get what I mean. Like I can very quickly try to alter this, and if I just pick random things on off the top of my head, I don't know, like this is probably not going to work. I don't know. I have to check. I'd have to go through the process, and if I get stuck, I would tweak the problem to make it work. I mean, there's always a way to I can tweak it, but it'll be a different problem. What I'm trying to say is very quickly I can design a question that I don't know how to do. Which is, right? These are kind of very, very strange problem types. Anti-differentiation is a very, very brittle kind of thing, problem type. Unlike derivatives. Derivatives is like, hey, I've got the chain rule. I can differentiate whatever. But anti-differentiation, it's, there's a lot of very small looking problems that I cannot do, that I literally cannot do. Should we look at another example of this type where at least immediately not all the x's go away? So I've got this one. Integral x times root 2x minus 1 dx. It seems like picking u to be what's in the radical is maybe going to be promising. So we'll do, yeah, u equals 2x minus 1. The derivative is just a 2, right? Because the 2x differentiates to a 2. And normally there'd be a minus, but the 1 differentiates to a 0. So I just didn't write in minus 0. Solve for dx as usual. So multiply both sides by dx. You have du is equal to 2 dx. Divide both sides by 2, and you have du over 2 is equal to dx. Okay, so there's sort of some of the usual steps. You got to pick a u, you have to kind of, well, you got to guess, and then we've solved for dx. Now we can make some replacements. So there's the original question here again. Integral x times root 2x minus 1 dx. Let's make, I just copied the original question up there. I just wanted a copy of it after the work that we discussed so that the slides make sense if somebody's downloading these and not listening to the audio. But we'll make some replacements. So we'll replace what we can. So inside the radical was a 2x minus 1. I replaced that with a u. The dx was replaced with du over 2. And we're looking again after replacements for cancellations, but nothing's going to cancel here. I mean, there's an x. That's a problem, right? We've got x's and u's. This mix of variables is no thank you. So we have this kind of issue again of like not all the x's went away. And if we just left it to our kind of recipe card yesterday, we'd toss this out, try a different u, something like that. But we've got this new idea we want to try. It's like, wait, what about, can we go back to right there? And is it easy enough to solve for x? In this case, we're going to solve for x. In the last problem, we solved for x squared. And it's not so bad to solve for x here. So let's take a look at, starting from this, our choice of u equals 2x minus 1. To solve for x, I would add 1 to both sides, right? U plus 1 is equal to 2x. And then one last thing to solve for x here, divide both sides by 2. So you have u plus 1 over 2 is equal to x. So we'll take this copy of the problem that we have so far, and where there was this x, we were hoping there wasn't an x because the problem would have been so much nicer. It's going to be more tedious because there is this x, but we can deal with it. I think is the point, is that we can replace the x that appears right here with this fraction u plus 1 over 2 instead. So there's the, just to, again, because this discussion is getting in the way, I just made a copy of this so that this makes sense if people just download the slides. But I replaced the x that's right there with u plus 1 over 2 because that's what we just saw that x should be equal to. And then from this step to the next couple steps, I will just say that there's a lot of valid ways to organize the algebra. I mean, there's a lot of mistakes sometimes people make in organizing the algebra as well, but there's a lot of different ways to take the next couple steps. So if your natural thought process of, oh, I would have done it this way, looks different than what I have, that's okay, right? If in the end we have the same final answer, I mean, everything, or, answers that are algebraically equal, then that'll be fine. But just to, here's how it's kind of what do you see first, right? And what I saw was I just saw the 2, and this, all of these things are multiplied, right? You've got the denominator 2 and this denominator 2. So I simplified that multiplication as a 4. The u plus 1 I just kind of left in the numerator. This root u, I should have explained it back here. I didn't even, I had written that as a u to the 1/2 and copied that over. The du is just kind of off to the side. So I guess all I really did going from here to here was simplify the 2 times 2 in the denominator. And then, this is for better or worse, there's lots of different ways to do this. What I chose to do was I chose to rewrite the fraction u plus 1 over 4 instead as a u over 4 plus a 1 over 4. But then, because it's 2 separate terms and I need to respect what the order of operations is trying to say, this now has to be in parentheses. And then what I chose to do was I distributed this u to the 1/2 to each of these terms. And that, at least in principle, is sort of like what we saw in the previous question. It's just now it'd be numerator stuff multiplied together. So u to the 1 times u to the 1/2 is u to the 3/2. And then it should all be over a 4. But I just, instead, because I didn't, I just don't want to have too many fractions with the variable inside it. So I just pushed the 1/4 just next to it. And then this one requires less explanation, I guess. The 1/4 times u to the 1/2. I just wrote the two things next to each other. Again, there's other ways to organize this algebra. There's so many ways to organize the algebra properly here. So it's just, you got to make a choice. And if your choices are a little different, then fine. The bigger story here isn't about how to do this algebra. It's let's see the process through here. Now we should anti-differentiate each of these two terms separately, right? The plus signs. When I see those plus signs inside an integral problem, I like that because integrals can be challenging. So the fact that I get to break it down one term at a time, that's nice. That happens with pluses, but not with times signs. So we'll anti-differentiate. Let's copy the 1/4 and then raise the exponent by 1. So that's why there's a 5/2 divided by the 5/2. This exponent of 1/2 raised by 1, so you have a 3/2 divided by 3/2 plus c. And then, cool, we've done, I think, the challenging step. One of the most challenging steps in this process is actually finding an antiderivative. So going from here, where there was an integral symbol, to here, where we're reporting what the antiderivative is. Now we have a nice step. The final step is nice. We just replace u. So the u's here and there should be replaced with 2x minus 1 from the beginning. So let's pause here, see if we're okay with this one. Any questions of any kind? Again, the algebra can be organized, lots of different ways. So I don't know if it's very fruitful to say, well, what if you do the algebra this way? I mean, those are some algebra choices that you make. I think the bigger overall question is, wait, if you want to talk about, wait, how did you do your algebra step? Those are, I think, the more important questions to clear up right now. Or what happened here? Or, like that. It's those kinds of things that I think are key to deal with, if there's any of those kinds of things. Okay, well then, how about, can I have you work on this one for a little while? If there's a bit of a pattern that I want you to notice, that for these that we've seen, generally the content inside the radical, so don't include the radical itself. I'm not doing u equals root x cubed plus 2, but just the stuff that's inside the radical. That seems to be a promising choice. I thought I'd reveal, just that's going to work. So give it a try. See what happens if you do u's equal to x cubed plus 2. Even if after some kind of cancellations, even if all the x's don't go away, well, see if our new sort of slight modification of the old technique, does that get you anywhere? Just reveal up to what my dx was. Let's make sure that that's looking okay. So I did some substitutions, canceled an x squared on top and bottom. I was left with this uncancelled x cubed on top. So I dealt with that x cubed by taking u equals x cubed plus 2, subtracting 2 on both sides, and then you can replace the x cubed with u minus 2. And so then, now what? Again, this is a place where your algebra steps might look different from mine. So there's really, in principle, lots of ways to deal with all this stuff. First of all, I thought let's just, this time around, and it looks a little different than how I did it last time. I just took that 3 that's in the denominator and pushed it all the way in front. It's still in the denominator, so it's a 1/3. I also, there's other ways to do this, but what I did was I broke up this fraction. When you have pluses or minuses in the numerator, not in the denominator, but in the numerator, you can split it up, right? And you can have u over root u, and then 2 over root u, and I still have this minus sign there. This is not the only way to do it, but it's just one approach that's kind of get us to a place where we can deal with this. Now, I don't want to anti-differentiate this and this term just as written yet because it's stuff in the numerator and denominator. So what I chose to do was I said, you know what, u to the 1 divided by u to the 1/2, right? So when you divide things with the same base, you subtract the exponent. So the exponent of 1, exponent of 1/2, you subtract from each other, you get a 1/2. When you have a root u in the denominator, you could write that as a u to the negative 1/2 power. So there's other ways to get to a step that looks like that. There's lots of different ways to get the algebra to get you to this spot. Maybe you didn't put the 1/3 outside. You might just have a 1/3 right outside the parentheses here, or you might have it in a distributed form where there's a 1/3 attached to each of those separately. But now each of these look very promising to anti-differentiate. So the u to the 1/2 should anti-differentiate to be a u to the 3/2 over 3/2. I copied the minus sign and the 2, and then the u to the negative 1/2, that exponent of negative 1/2, when you add 1 to it, you have an exponent of positive 1/2, divide by the new exponent of 1/2. And since this is the step where the anti-differentiation occurred, there's this plus c. And as a final step, now that the anti-differentiation has been done, this is a difficult step, I think, to think through. All these, all the antiderivative rules that we had prior to substitution. So then, then the last thing to do is to replace the u's. So the u's here are replaced with x cubed plus 2. Let's just pause for a moment. See, does this, again, your algebra steps can look different from this and still be valid. In fact, not even every time in the 3 questions we've gone through, I have not done the algebra exactly the same every time, just to try to kind of warm you up to different ways the algebra can look. Usually the thing people want cleared up, I'll just start kind of answering because I have done this question in the past. People are like, wait, how did that become this is usually the question. So u over root u, this is u to the 1 over u to the 1/2. And when you have things with the same base, normally, so same base when you're multiplying things, you get to add the exponent. So same base, but you're dividing the things, you have to subtract the exponent. So this 1 exponent and then the 1/2 exponent, when you subtract, that's why this exponent is a 1/2. And it's not the only way to think of it. Some other people prefer this thought process of the denominator is a root u, but another way to write u is root u times root u. So when you cancel a root u on top and bottom, you're left with just a root u, and another way to write that is u to the 1/2. That's another way to get to that stage. So that's the usual question that I remember last time I taught the class, so I just thought I'd address it in case that was the question you had. Okay, what I'd like to do then is I will put these problems up. Sorry, they're a little scrunched here, but I wanted this text, okay? Not all of these 8 problems are done by substitution. So for some of these questions, you don't do a u equals, right? Like so all of the questions are going to require anti-differentiation at some point. Either it's right away or right after a little bit of algebra tweaking. That anti-differentiation might occur in the middle of the problem, like what happens with substitution. But some of these will require substitution, some of them won't. But that's kind of, it's good to, so I'm mixing together. Normally on this day in class, I would normally ask people to bring the book. I don't know if people have it at home, so I found some problems from online and I made a couple of my own. And I just kind of mixed them up. So some of these require substitution, some don't. I just want to give you a chance to try these. And then, if you want a hint on any of them, you let me know. Or you want to check your work on one of these. Okay, I've got 3 minutes left. So what I'm just going to do is kind of a quick round of announcements. First of all, for these problems, I plan on writing up a set of solutions, hopefully by the end of the day. I kind of have a lot going on. But this down here in red, if you download the slides, is a link. It's a link to where I'm going to eventually post the file. Right now, you can click on the link, it'll just say file not found. So I kind of already just future created that, just so that people, if they download the slides, they're ready to go. The link doesn't work yet. Um, this is the up to this point is where next Thursday's exam covers up to. Um, the one thing that I think is just going to be a little different is people had noted to me it was stressful to upload a bunch of individual pictures, and there are ways to. So I what would be, I think, helpful based on the comments I received, both for all the students and for me, is to get a single file and specifically a PDF out of everybody. There are ways to do this. One of the tasks for me this weekend is to write a clear set of instructions that goes through how one can do that. And there's lots of different options, lots of free options. So I'm going to kind of get that all cleared up. And then finally, just kind of common reminders. Today's a Thursday, so please complete a quiz. And otherwise, I will see you later. So look for an email this weekend where I try to clarify all the things related to the exam and so on.